Let's do one more example. In this case, we're looking at a set C. It is equal to all vectors xy such that y is greater than or equal to x. We want to see if this set is a subspace of R2. Right? Now, we do know that this is clearly a subset of R2, right? This just has a bunch of two-dimensional vectors with certain properties. That set of two-dimensional vectors with certain properties, it must be a subset of all the possible two-dimensional vectors. So if we want to determine if this is a subset, or I'm sorry, a subspace of R2, we need to check if this is closed under addition and closed under scalar multiplication. And by the way, it might be helpful to draw this out first, especially in two-dimensional space. If you have a chance to draw it out, it can make things easier. To plot an inequality like this, y greater than or equal to x, you'd first plot the equality. So the line y equals x is this line right here. And then you're going to shade one side of it. And if you're not sure which side to shade, plug in a point and see if that point makes the inequality true. So if I plug in the point 0, 2, the inequality is true, right? 2 is greater than or equal to 0. And so I would shade this side. So I'm checking if this region is a subspace of R2. Okay? That half of the plane. So if you look at this, you might get a sense for whether or not we are closed under addition, we're closed under scalar multiplication. Viewing the geometry can make it a little bit easier. So let's start by checking if we're closed under addition. And I think that if I take two vectors in this half of the plane and I add them together, the result will still be on that half of the plane. All right? So if you're confident and if you think you know what's going on, you can skip the example part. So I'm going to do that. I'm going to skip. I'm not going to look at two individual vectors and see if it works out. I am going to go to the general solution right now. So let's take two vectors in this set, in set C. Okay. Then we know that y1 must be greater than or equal to x1, and y2 must be greater than or equal to x2. Right? That's what it means to be in set C. Set of all two-dimensional vectors have this property. Okay, but what about the sum? So the sum of the two vectors, I add x1 plus x2 to get my first component, y1 plus y2 to get my second component. And, well, if this was bigger than x1, and if y2 was bigger than x2, then y1 plus y2 has to be bigger than x1 plus x2, right? I can't add two smaller things and get something bigger than the sum of two bigger things, right? Which means that my sum is in set B. Okay? Which means we're closed under vector addition. The first one's checked off. It might be a subspace, right? I'm sorry, not set B, set C. Set C. Set C might be a subspace of R2, but we don't have enough information yet. We have shown it's closed under addition. We still need to determine if set C is closed under scalar multiplication. And again, I'm looking at this and I'm pretty confident that it is not closed under scalar multiplication. The picture really helps me in this case. Because if I take some vector in the space, what I could do is I can multiply it by a negative scalar of that same vector. And then I'd be outside, wouldn't I? So let's find that counterexample. So actually, I like the word take. Take. So I need something in this space. I could keep it real simple. So let's do 0, 1, right? Certainly this is in set C because the y value 1 is bigger than the x value 0. So it satisfies this condition. And I'm just going to take a negative scalar. I really could have taken any negative scalar, I think. But I'm going to take negative 2. So if I do the scalar vector multiplication, I get 0, negative 2. And that very clearly is not in C. The y value is not greater than or equal to the x value. Okay, now the y value is smaller. Negative 2 is smaller than 0. So C is not closed under scalar multiplication. So C is closed, our set C is closed under addition, but not under scalar multiplication. In order to be a vector subspace, it needs to be closed under both addition and scalar multiplication. Since it's only closed under one, C is not a subspace of R2.